LIGO is the abbreviated form of Laser Interferometer Gravitational Wave Observatory. LIGO is used to detect a gravitational wave. A gravitational wave is nothing but a ripple created in the fabric of space-time. It is the world's largest gravitational wave observatory and the most sensitive measurement device constructed to date. It is a complex structure made with a high level of correctness and is recognized as one of the modern marvels birthed by engineering. The idea of constructing a LIGO was conceived by Rainer Weiss as a way to detect gravitational waves, as Einstein had earlier predicted the existence of extremely small ripples in space-time fabric in his theories of relativity. Later, in 2017, Rainer Weiss shared the Nobel Prize for Physics along with Barry Barish and Kip Thorne. LIGO detects the gravitational waves using principles of interference of light and properties of space and aims to develop gravitational wave observations as an astronomical tool in space research. It has now been confirmed that gravitational waves that were produced when two neutron stars collided with each other 130 million years ago in the constellation of Hydra. LIGO consists of two separate L-shaped detectors, one located in Louisiana and the other in Washington state of the USA, over 3,000 kilometers apart. They detect gravitational waves using lasers and multiple mirrors to observe the changes made in the space-time fabric by gravitational radiation. Each station keeps record of change in the distance between the two mirrors, each placed at either end of a 4-kilometer long tube called interferometer. A laser beam is made to bounce back and forth between the two mirrors of the tube. The beam tube of the interferometer are placed perpendicular to each other, and the atmosphere is evacuated inside, so that the density of the air inside the interferometer is as small as a trillionth of the density of atmospheric air. There are vacuum chambers which are cylindrical in shape called horizontal axis modules, or just HAM to put it simply. HAM 1 contains the laser beam at the front end of the interferometer. The beam produced is then made to reflect between a series of mirrors in HAM 2 and HAM 3. It sharpens the frequency of the beam produced by the laser and thus increases its power by resonance. The beam then reaches a central beam splitter, which is another mirror which splits the light into half and then sends the light beam equally divided into each of the two tubes of the interferometer. Each arm amplifies the beam by reflecting it over 300 times between two mirrors called test mass mirrors at each end. The mirrors are suspended by a 4-stage pendulum to eliminate any errors that may be caused due to seismic aberrations or other vibrations. The beams returning from both test mirrors are made to recombine at the beam splitter exactly out of phase. As the phase difference of the two beams is 180 degrees, they cancel each other out to produce no output signal as observed by the photodetector. When there is presence of a gravitational wave though, the two arms of the interferometer stretch and compress as a result of space-time fabric being stretched and compressed. Due to this, the two laser beams will not exactly be out of phase and some light reaches the photodetector. This helps to detect the presence of gravitational waves. This is done at both stations to double check the presence of a gravitational wave. Thank you.